So in the previous video, we talked about the center of momentum frame, right? And specifically, we saw that the length of the vector, right, before the length of the vector, right, the magnitude of the velocity before and after the collisions, they don't change, right? We don't know which direction at the moment, but we know that the magnitude of the velocities do not change. So, of course, we like to rederive, right, the 1D elastic collision. We'd like to revisit it and make sure that it gets us the same result, right? If not, there's something seriously wrong with our calculations. So, in the 1D elastic collision, right, the vector equations just become scalar equations. So we have the following, and the result that we got just now was that the square of the velocities do not change, right? And in 1D, it's just the real number squared, right? Because in 1D, the velocity is only described by a single real number. It could be negative or positive. That's why the square is important, right? So it's wrong to say UB is equals to VB, right? Because they could differ by a minus sign, right? And this will still hold true, okay? But there's something nice we see over here, which is that because we're in one dimension, right? Because we're in one dimension, the equation 95 is only satisfied in two ways, right? One is UB is equals to minus VB, and one is UB is equals to VB, right? Either one of them is true. And it turns out that because previously we said that we're in the center of momentum frame, and we know that in the center of momentum frame, right, if A is to the left of B, right, in the center of momentum frame, B must be moving to the left, right? There's no way for B to be moving to the right. If they're going to collide, right, B must be moving to the left towards A, and A must be moving to the right. So that would mean that UB must be less than 0, right? And likewise, this is before the collision, right? After the collision, after they hit each other, VB must be moving to the right. So VB must be greater than 0, right? All of this is assuming we define rightward as positive. So that basically means that we are working with the first solution over here, right? The second solution can be rejected, right? Because the signs must flip. The signs of the velocities must flip. And so yeah, so we arrive at the following result, right? Equation 97 tells me that in 1D elastic collision analyzed using the center of momentum frame, right, the velocity just flip, right, in the center of momentum frame. So now if we go back into our lab frame, right, then the velocity the velocity of A is equals to the velocity of A in the lab frame is equals to the velocity of the center of momentum in the frame, right, plus the velocity that the center of momentum frame observes A to be, right? And if we plug our results back in, right, I won't go through all the gory detail, but if we plug the results back in, we basically get back the same results, right? We basically get back the same results. And you may be wondering, wait, didn't it seem like we just went through a lot of work, right, to basically rederive the same results? It seems like the first method is easier, right, and the lab frame is easier. And you'll be for the 1D elastic collision, you'll be right actually. The first method was easier, but however, right, what I said previously about the length of the vector staying the same, right, this result over here, this result will be indispensable when we go to higher dimensions, right? So for 1D it's quite obvious, it's just flipping, but for higher dimensions this result is indispensable, and that's what we'll talk about now.